Hi guys, in this lecture we will be starting with induction machine and we'll take a look at what kind of questions can be asked in induction machine and how to tackle such kind of problems. So the first type of problem that is generally asked in GATE is based on speed of the rotating magnetic field. So in this what you need to remember is speed of magnetic field is equal to 120 into F by P with respect to apparatus. Now what is meant by this statement? Suppose we connect a supply to the stator winding, okay? Then stator will set up a magnetic field. That magnetic field will rotate at 120 F by P with respect to stator. Apparatus means the place where the winding is wound. So we know that stator winding will be wound on the stator. So it will rotate at ns with respect to stator. Now suppose we have a three-phase winding on the rotor and we apply a F frequency supply to the rotor. Then the rotor winding will create a rotating magnetic field which rotates at 120 F by P with respect to rotor. Okay. So the magnetic field will rotate at 120 F by P with respect to the part where the winding is actually connected or winding is actually wound. Is it fine? Now the second thing, speed of one magnetic field with respect to another. We know that there are two magnetic fields in any rotating machine. So both must be stationary with respect to each other or their relative speed must be 0. Then only a steady torque can be produced, otherwise the torque is oscillating and it does not cause rotation of the machine. These two things you need to remember. The next is the concept of relative speed. Relative speed is actually actual speed minus speed of reference. Here everything is vector, that is you have to consider the magnitude as well as the direction. So see, speed is always measured with respect to earth, or in this case, in case of machine, you can call it stator because stator is stationary. So actual speed means with respect to stator. What is meant by speed of reference? Suppose you are calculating speed with respect to rotor. So reference speed will mean the rotor speed. If you are calculating speed with respect to stator, reference speed will be the speed of stator, which is actually 0. If you are calculating with respect to stator magnetic field, the speed of reference will be equal to speed of stator magnetic field. Is it fine? So let us see the problem that is asked. The rotor winding of a 6-pole 3-phase slip ring induction motor receive a 3-phase 50 Hz supply which produce an air gap MMF rotating in the clockwise direction with respect to rotor. The rotor itself is being rotated in the clockwise direction at 400 RPM. The frequency of voltage induced in stator phases. So as you can see, we are applying the supply voltage to the rotor winding. So what is synchronous speed? 120 into F50 by 6. That is 1000 RPM. So this is the speed of magnetic field with respect to rotor. Is it fine? As I told you, the speed is with respect to the place where the winding is wound. Here the winding is on rotor, so speed is with respect to rotor. Now, this is the case of a inverted induction motor. In inverted induction motor, what happens is, the supply is on rotor and the induction is taken on the stator. Now it is saying, the rotor itself is rotating in the anti-clockwise direction at 400 RPM. Okay? And the magnetic field rotates at 1000 RPM in clockwise direction. So as you can see, the direction of rotor and the magnetic field is opposite. Magnetic field is anti-clockwise. and the magnetic field is clockwise and rotor is anti-clockwise. Now we know relative speed is equal to actual speed minus reference. Here relative speed with respect to rotor is 1000. Actual speed means speed with respect to stator we do not know. But speed of rotor is minus 400. Why minus? Because if clockwise is positive, the anti-clockwise can be taken to be negative, which means actual speed is 600 RPM. So this is the speed of magnetic field with respect to ground or stator. Now this is the speed which will cause induction in the stator winding. So I will call it 120 Fs by P. Fs is the frequency of stator voltage. So what will be Fs? 600 into poles is 6 by 50. So how much will it be? 6 by 120. It will be 30 Hertz. That is, the frequency of induced EMF in stator is 30 Hertz. Let us look at one more problem of the same type. It is saying a 3-phase 50 Hertz induction motor has a full load speed of 960 RPM. We need to find the number of poles. See, number of poles can only be determined from synchronous speed, but here we have a rotor speed and not the synchronous speed. So you have to take the synchronous speed as the nearest possible speed to the rotor speed. So what is the nearest possible speed? That is your 1000 RPM. So 1000 RPM is basically equal to 120 into 50 by P. So this P will come out to be 6. That is, the machine shall have 6 poles. Next it is asking slip frequency. For that we need slip. Slip is Ns minus Nr by Ns. So slip will be 1000 minus 960 by 1000, that is 0.04. So what about slip frequency? It will be SF 0.04 into 50. That will become 2 Hertz. Okay, 50 into 0.04 will be 2 Hertz. Next it is asking us different speeds. So first is speed of rotor field with respect to rotor. Now here, when it is not given, this supply can be assumed to be on stator. So speed of stator field with respect to stator, how much will it be? Ns, that is 1000 RPM. As I told you, speed of both magnetic fields should always be same, otherwise there will be no torque production. So speed of rotor field with respect to stator will also be 1000 RPM. Now we know rotor speed is actually 960 RPM. So what is speed of speed of rotor field with respect to rotor? It is actual speed 1000 minus reference speed, that is 960, 40 RPM. So speed of rotor field with respect to rotor is 40 RPM. With respect to stator is 1000 RPM. With respect to stator field, as we know both fields should be stationary with respect to each other, this shall be 0. Both fields should not have any relative motion for steady torque production. Moving on to the next problem, it is saying a 4-pole 3-phase slip ring induction motor is coupled mechanically to a synchronous motor having 2 poles. Whenever you see this concept, mechanical coupling, it means rotor speed of both the machines should be same. Their rotors are coupled together, so they have to rotate at the same speed. Now we know whenever we have a synchronous machine, it will have a fixed speed, that is 120 F by P. So what is the speed of synchronous motor? It is 120 into 50, because it is saying 50 Hertz voltage source, by 2. That is 3000 RPM. Now synchronous machine cannot rotate at any other speed. So the rotor speed of synchronous machine will also be 3000 RPM. Now rotor of synchronous machine is connected to rotor of induction machine, which means speed of rotor of induction motor will also be 3000 RPM. Now this is the rotor speed. But what about synchronous speed of induction motor? That is, I am interested in NSIM. That will be 120 into F by number of poles of induction motor. There are 4 poles in induction motor, so it will be 1500 RPM. Now let us see what it is asking. What will be the frequency of EMF at the rotor terminals if synchronous motor is driven in a direction opposite to stator magnetic field? Which means the rotor rotation is opposite to the magnetic field. So the slip is given by Ns plus Nr by Ns. When the magnetic field and rotor both rotate in opposite directions, the slip comes by addition. How? As I told you, when we take relative speed, we have to consider direction, and when we consider direction, opposite field will be taken with a negative sign. So relative speed will actually come by addition instead of subtraction. What I mean to say is, relative speed is actually actual speed minus reference. If actual and reference both are opposite, it will become plus. That is the concept. So here we know synchronous speed is 1500 for induction motor. The rotor speed is 3000 by synchronous is 1500. So slip comes out to be 3. So what will be the frequency? That will be SF. So it shall be 150 Hertz. Next is, synchronous motor is driven in the direction of induction motor stator rotating field, which means both are in same direction. In same direction, the slip will be Ns minus Nr by Ns, 1500 minus 3000 by 1500 minus 1. Usually in slip we ignore the negative sign, so slip will be 1. So frequency induced is SF, S into 50 or 1 into 50 is 50 Hertz. Next question, it is asking, if frequency of rotor voltage is 300 Hertz. So Fr is 300, which is equal to S into Fs, which implies the slip shall be 300 by 50, that is 6. If slip is 6, it should only come by Ns plus Nr by Ns. Now, we know that the rotor of induction motor is rotating at 3000 RPM. So, it means Ns will come out to be 600 RPM. Now, this synchronous speed is for induction motor, which is fed with a 50 Hertz source, but we do not know the number of poles because it is asking the number of poles. So number of poles will be 10. Okay, that means if induction motor is constructed with 10 poles and the rotor is rotated opposite to the magnetic field, the frequency induced in the rotor shall be 300 Hertz. Is it fine? The next type of question is based on torque slip characteristic. For that, you need to remember the torque expression. It is 3 by omega s V2 square R2 by s R2 by s square plus x2 square. This is when we neglect stator impedance. Okay. If you consider stator impedance, then you need to find Thevenin resistance and Thevenin reactance. Then this formula shall become 3 by omega s V2 square R2 by S over R equivalent plus R2 by S whole square X equivalent plus X2 square. Okay, that is the basic of the torque slip characteristics. Now, let us see the problem. A three-phase induction motor has a four-pole star-connected stator winding. So, poles is equal to 4. It is running on a 50 Hertz supply. So, we can calculate NS 120 into 50 by 4, which is 1500 RPM. The rotor resistance and standstill reactance are 0.1 and 0.9. The ratio of rotor to stator turns is 0.67. Now it is saying voltage is 200 volt between lines and it is star connected, which means phase voltage is 200 by root 3. So what about rotor voltage? It is 0.67 into 200 by root 3. Just like transformer, I have transformed the voltage from stator to rotor. Now it is asking torque at 4% slip. So torque will be 3 by omega s. How to calculate omega s? 1500 into, convert it to radian per second by multiplying by 2 pi by 60. V2 square, which is 0.67 into 200 by root 3 square into R2 by S. R2 is 0.1. Slip is 4%, that is 0.04 by 0.1 by 0.04 whole square plus 0.9 square. This will come out to be 40.48 Newton meter. Okay, that will be the torque at 4% slip. Now it is asking mechanical power, or we can say developed power. That will be torque into rotor speed. 40.48 into omega s. Now rotor speed is synchronous speed into 1 minus slip. So it will come out to be how much? 6.1 kilowatt. Okay. In the next part, it is asking us maximum torque. So for maximum torque, first you must understand the condition. Slip for maximum torque is R2 upon RE square XE plus X2 square. If you neglect stator impedance, that is you neglect RE and XE, it is R2 by X2. In such a case, the maximum torque is 3 by omega s V2 square by 2 into X2. Now let us find out the maximum torque. It will be 3 by 1500 into 2 pi by 60. V2 square is 0.67 into 200 by root 3 square by 2 into X2 is 2 into 0.9. So this will come out to be 63.5 Newton meter. Okay, that will be your maximum torque. What about speed at maximum torque? For that I need slip. Slip will be 0.1 by 0.9, that is 1 by 9. So what will be speed? Synchronous speed we calculated at 1500 into 1 minus 1 by 9, that is ns into 1 minus s, 1333.33 RPM. That will be your speed at maximum torque. Next it is asking maximum mechanical power or maximum developed power. For maximum developed power, what happens is, the slip for maximum power is R2 upon R2 plus RE square XE plus X2 square under root. That is the slip for maximum power. This will become R2 upon R2 plus X2 if the stator impedance is neglected. So in our case, what is the slip for maximum power? 0.1 by 0.1 plus 0.9, that is 0.1. At this power or at this slip, I need mechanical power. So how will you calculate mechanical power in such a case? For calculating mechanical power, what you need to do is, you need to calculate the air gap power. Okay. How to calculate air gap power? 3 I2 square R2 by S. So mechanical power will be 3 I2 square R2 by S into 1 minus S. So what will be mechanical power? 3 into I2 square. How you will calculate? That will be V2 square divided by impedance square. What is impedance? Impedance is R2 by S, that is 0.1 by 0.1, that is 1. X2 square 0.9 square into R2 by S, that is 1, into 1 minus S, that is 1 minus 0.1. So this will come out to be 8.93 kilowatt. So remember this thing, the condition for maximum mechanical power and the maximum torque is different. You have to memorize both the condition. In the next question based on the same concept, one thing I also want to tell you is that this is the most important concept in the induction motor. Most number of questions can be framed based on torque, so you need to be very well versed with this concept. Now it is saying the rotor resistance and standstill reactance of a three-phase induction motor are 0.015 ohm and 0.09 ohm. At normal voltage, full load slip is 3%. Estimate the percentage reduction in stator voltage to develop full load torque at 1/2 of full load speed. So this thing is very critical. Half of full load speed. Okay. It is not saying half of full load slip. It is saying half of full load speed. So first let us calculate NFL. It is NS 1 minus SFL, that is 0.97 NS. So what is half of full load speed? 0.97 by 2 NS, that is 0.485 NS. So what will be slip? 0.515. That will be the slip. Now it is saying we need to develop the same torque as the full load torque at half the full load speed. So let me say the voltage earlier was V, now it is changed to X into V. Is it fine? So what happens? Full load torque, what it will be? 3 by omega S V square. R2 0.015 by S is 0.03 by 0.015 by 0.03 square plus 0.09 square. This same torque should be developed at this slip at a reduced voltage. So 3 by omega S, let us say reduced voltage is X into V, into 0.015 by slip is 0.515 by 0.015 by 0.515 square plus 0.09 square. Now this V will get cancelled out, omega S3 will get cancelled out, this will also get cancelled out. From here we can calculate X, it comes out to be 0.77, which means the voltage becomes 77% or percentage reduction is 23%. which means if you reduce the voltage by 23%, you will get the same torque as the full load torque but at half the speed. Now it is asking the power factor in such a condition. So remember, in case of induction motor, power factor is always R2 by Z2, which is 0.015 by 0.515, sorry, R2 by S, 0.515. Now Z2 will be 0.015 by 0.515 square plus 0.09 square under root. That will be the power factor. It comes out to be 0.3. Okay. That is, in such a case, the motor operates at a very low power factor or it consumes a large amount of reactive power. Moving on to the next problem, it is saying an 8-pole 50 Hz 3-phase induction motor has an equivalent rotor resistance of 0.07 ohm per phase if its stalling speed is 630 rpm. So first let us calculate NS. It will be 750 rpm. Now what is meant by stalling speed? How will the motor stall? The motor only stalls when it is not able to produce the torque equal to load torque, or we can say the load torque is more than the maximum torque that can be produced by the rotor or the machine, which means this is the speed at maximum torque. So this is the speed for maximum torque, that is 630 rpm. Now it is saying how much resistance must be included per phase to obtain maximum torque at starting. So for that, first let us calculate slip for maximum torque, that is Ns minus Nr by Ns. Okay, this slip comes out to be 0.16. Now we know this is equal to R2 by X2. R2 is given as 0.07 by X2, which means this X2 will come out to be how much? 0.4375 ohm. Now it is saying that maximum torque should occur at starting. For two torques to be equal, their slip must be equal. If the slip is equal, it means the slip for maximum torque should be equal to the slip at starting. At starting, the speed is 0, so slip is 1. Which means after adding external resistance, what happens is the slip for maximum torque becomes equal to 1. So this will be 0.07 plus whatever external resistance you have added by X2. X2 does not change. 0.4375. From here we get external resistance as 0.3675 ohm. Okay, that is how you can control the torque at a particular speed by inserting external resistance. In the next problem, it is saying a 3-phase 50 Hz 12-pole induction motor has star connected rotor and resistance measured across any two slip rings is 0.04 ohm. As I told you in synchronous machine also, when the winding is star connected, the per phase resistance is measured upon 2. So per phase resistance would be 0.02 ohm. Next it is saying its full load slip is 0.02. Okay. The torque required by the load varies as the speed squared. Okay. The torque slip curve is assumed to be straight line in normal operating region. So what happens from SFL to SMT, or usually from even 0 to SMT, the curve is straight line, or we say torque is proportional to SV square by R2. This you need to remember. In normal operating region, torque is proportional to slip and voltage square, and inversely proportional to rotor resistance. And in the high slip region, that is from SMT to 1 or near to 1, the torque is inversely proportional to slip. Okay, and it is directly proportional to R2, or we can say torque is proportional to R2 by S. That is why starting torque increases with increase in rotor resistance, whereas full load torque will reduce with increase in rotor resistance. So we are assuming linear curve, that is torque is proportional to SV square by R2. The resistance to be inserted in rotor circuit to reduce the full load speed to 350 RPM. That means I need to make the new speed as 350 RPM. So first let us calculate NS. 120 into 50 by 12, that is 500 RPM. So what is the new full load slip? 500 minus 350 by 500, 150 by 500, 3 by 10 or 0.3. Okay, that is the new slip required. Now I know torque is proportional to omega square, so what I can suggest, if voltage is not changing, S by R2 is proportional to omega square. Is it fine? So what is first speed initially? Now it is 350 RPM. Initially it would be 500 into 1 minus 0.02, that is 490 RPM. So we know old speed, we know new speed. We need to find the external resistance. So what I will do is S1 by R1 into R2 by S2 should be equal to N1 by N2 whole square. R1 is the old resistance, R2 is the new resistance. So initial slip was 0.02. Resistance was how much? 0.02. New resistance is 0.02 plus some external resistance. New slip is how much? 0.3. Old speed was 490. The new speed is 350 RPM. If this thing happens, what I can do is I can calculate the value of R external. It comes out to be 0.568 ohm. This much external resistance is required. This can also be covered under speed control of induction motor, because we are controlling the speed by inserting external resistance. Next, let us see a similar problem. A three-phase wound rotor induction motor develops a maximum torque of 4 times the full load torque, which means it is saying T max by T full load is 4. In such questions, you have to remember one thing, that torque at any slip upon maximum torque is 2 upon S upon SMT plus SMT upon S, where S is the slip at which this torque T occurs and SMT is the slip for maximum torque. That is the direct relation between torque at any slip and the maximum torque. Now it is saying it is 4 times the full load torque at a slip of 0.2, which means slip for maximum torque is 0.2. Now per phase rotor resistance is 0.04. The stator resistance and rotational losses are negligible. First we need to find the slip at full load torque. This I can do directly. T by T max is equal to 0.25, because this is the inverse ratio. 2 upon, we do not know about the full load slip, but we know the slip for maximum torque. This will cause us a quadratic equation. It is equal to 8. So SFL square minus 8 SFL plus 0.04 equal to 0. Okay. 2 by 0.25 is actually, oh sorry, it will be 0.2. So it will be 8 into 0.2, that is 1.6. So from here we can calculate SFL. It will come out to be 0.0254. That is the slip for the full load torque. Next it is asking if stator resistance is considered, would the speed at slip at full load torque be smaller or higher? If you consider the stator resistance, slip is inversely proportional to resistance. So it will be reduced. Slip will be lower if you consider the stator resistance. Next it is asking calculate the value of external resistance to be inserted in rotor circuit to obtain maximum torque at starting. Again we are facing same problem. It means we have to make SMT equal to 1. Now initially the slip for maximum torque is 0.2. Rotor resistance is 0.04, which means the rotor reactance would be 0.2. Now when slip becomes equal to 1, which means 0.04 plus external resistance upon reactance must be 1, which means external resistance is 0.16 ohm. Okay. So whenever you see this kind of condition, that slip for maximum torque or maximum torque becomes equal to starting torque, you just equate slip for maximum torque to be 1. In the next problem, it is saying a 10 kilowatt 6 pole 50 Hertz 3-phase induction motor has linear torque slip characteristic, which means torque is proportional to SV square by R2. Between 0 torque and maximum torque, the slip at which maximum torque of 520 Newton meter occurs is 0.2. See, the curve between torque and slip is given to be linear, like this, and it is equal to 520 at a slip of 0.2. If such a thing happens, what is the slope? It is 2600, or we can say torque is equal to 2600 S. Now it is saying mechanical losses are 600 watt. Find the speed at which motor would run when delivering the rated shaft power, that is 10 kilowatt. If shaft power is 10 kilowatt, what is developed power? It is shaft power plus rotational loss, that is 10 plus 6.6, 10.6 kilowatt. Now we know developed power is equal to developed torque, which is 2600 S, into speed. Speed is how much? 120 into 50 by 6, that is 1000 RPM, into 2 pi by 60. I am converting it to radian per second, into 1 minus S, because speed of rotor is synchronous speed into 1 minus S. Based on this, I can form a quadratic equation, which is S square minus S plus 0.03893 equal to 0. From here, the slip comes out to be 0.0405. That is the slip for the case of motor which runs at rated shaft power. So from here I can calculate speed. 1000 RPM is synchronous, into 1 minus S, which becomes equal to 959.5 RPM. Is it fine? So that is the speed when the motor runs at rated shaft power. So these are some of the concepts related to the torque and the slip characteristics which you always need to remember. The next concept is for stability of an induction motor. Now for stable operation, the condition that you need to remember is the slope of the load torque curve must be greater than the slope of electromagnetic torque or the motor torque. Okay. So what happens is the operating point of any motor is decided by intersection of electromagnetic torque and load torque. But whether that point is stable or unstable is decided by the slope. Here, whenever you are taking the slope, you have to consider the sign also. So let me show you how. See, in the first curve at A, this will be the slope of dTL by dN. But the slope of dt by dN is negative because it is decreasing. We know negative value is always less than a positive value. Hence, point A is stable. The slope of load torque curve is positive, whereas the electromagnetic slope is negative. If you see here at B, this is the slope for electromagnetic torque and this one is for load torque. The slope is basically given by tan of angle made with the horizontal axis. So as you can see, electromagnetic tangent forms a higher angle. If it forms a higher angle, it has a higher slope, which means dTe by dN is greater than dTL by dN. Hence it is unstable. In the next one, if you see, this is the slope for electromagnetic torque, whereas this is the slope for load torque. The slope for load torque is higher than electromagnetic torque again, so it is stable. If you see here, this is the slope for load torque, slope for electromagnetic torque. Now as you see, the slope for electromagnetic torque is more steep, but it is negative. That is, it has a higher negative value. Slope being negative means the curve is decreasing. So it means again dt by dN is less than dTL by dN. Here the slope has a higher negative value, so it is lesser than the load torque. So again it is stable. Is it fine? The slope being less means it is more negative. So that is how you can judge the stability of any operating point of induction motor, just by observing the slope of the electromagnetic or the motor torque and the load torque. Okay. So this will be all from this lecture. In the next one, we will see more problems based on induction machine.